Alex, I think we can start, right?
I think we can. I still see people arriving. So I was waiting, but maybe, yeah. I don't know. What do you, yes, let's start. People, it's slightly arriving yet, but.
There's just some.
I see a small drop of people arriving, so. Okay, now.
We can start slowly.
Yeah, let's slowly start. Hello to everybody. This is the last lecture of this bunch of this session, let's say, of the Hitchhiker's Guide to the Condensed Matter and Statistical Physics. And for us, it's a pleasure to have here Juan Carrasquilla. Sorry, I should do it. And Juan Carrasquilla, now it's a faculty member at the Vector Institute. And it's also assistant professor at the University of Waterloo, if I read it correctly. He's working at the intersection between condensed matter, quantum computing, and machine learning. He's there in the middle. And he's a former diploma student of the ICTP. He's a success history for our diploma. And also a former student of PhD here at CISA, right? Always interested. From that, I think he has moved and starts doing several postdocs in the US, and now he's at Waterloo. So please, Juan, whenever you want, you can start.
Okay, thank you, Alex, for the introduction. Yeah, so it's a great pleasure to be at ICTP, to be back at ICTP, although this is an online talk. I'm always very happy to come. So I want to tell you about recurrent neural networks and how we've been using them for many body physics. So the first part is going to be about basic notions, and yeah, let's just get started. And so here are my my people funding my research, and the Vector Institute on University of Waterloo as well. So what are recurrent neural networks and why they're useful and why we think they're powerful tool to study many body physics? So let me tell you first what they are. So some generalities about what they are. So they're a family of neural networks that are naturally suited for processing sequential data. So this is how people talk about this RNNs, but you can process any data basically. But in principle, they're naturally suited for processing data that comes in a sequence or in an order, right? And so the sequence that I'm going to be using throughout my talk, if you want, is like a sequence of, say, spin variables, sigma 1, sigma 2 through sigma n. And you can imagine them, they're kind of like placed on a line, if you want, okay? Or you can think of this index I, 1, 2, 3 through n as time, for instance. And so the idea is that recurrent neural networks can typically scale much better to longer sequences than would be practical for other neural network architectures that you may have seen already last couple of weeks, like the restricted Boltzmann machine, which I'm sure you've seen last week, and so on. So there's this specialization for sequences with the RNN or for the RNN. And so this is part of like this, if you want, this conceptual idea that you can, by exploiting the structure of the problem, that you can make progress computationally, right? Like, and so we're going to be using this idea a lot. and people in machine learning use it all the time, right? Like that when you have a problem, you want to see what's the structure of the problem, and you use information about the problem to solve it, right? And this is something that we in physics do all the time. We use symmetries and so on, and this, if you want, enriches our understanding of the problem, but also it saves us, if you want, computational time. And so we do the same in machine learning, or people have been using this idea in machine learning as well. So most recurrent neural networks can process sequences of variable length. That's important. So this sequence that I have here, this vector sigma, can have, say, either 2 spins or n plus 1. And this architecture can process all those variable length sequences. So that's important, like for instance, in language translation and in general in natural language processing, which is one important task people in machine learning are interested in. So what to do? So to go from multi-layer neural network, such as like the RBM or the restricted Boltzmann machine that you have seen last week, I believe. What you do is you share parameters across different parts of the model, okay? So, and I'm gonna explain what this is in a little bit. And this is also what people use in computer vision in another famous architecture called convolutional neural network, okay? Which is right here as a CNN. There's this idea also very popular in physics and in machine learning, which is share the parameters of a model as you say process things over time or spatially, right? Like that you share the parameters, and this makes the parameters or the neural net more compact, but also more efficient at processing some sort of data. Okay, and so if we compare this so-called feed-forward neural networks, such as the restricted Boltzmann machine, so what you have is something like this, where each input, say sigma 0, sigma 1, sigma 2, sigma 3, is processed with their own set of parameters, right? Like, so for instance, I have highlighted here sigma 0 and sigma 3, and as the information about these variables is processed through the architecture, in this case vertically, you process sigma 0 with its own set of parameters, right? Like which I denote here in yellow. Whereas sigma 3 is processed with a different set of parameters here in purple. Okay, and so that's how you do it in a feed-forward neural network. But in a recurrent neural network, you do something a little bit different, right? Like you process sigma 0 with variable w, for instance. I'm gonna be explaining all these plots in a little bit more detail later, but the important thing I want to highlight here is that you process this sigma 0 with parameter w, and then you process sigma 1, and then you reuse the same parameter w, right? Like and so on and so forth for sigma 2 and sigma 3. So each input is processed through the same parameters, say u and w, and u, like where u are those here. So I'm going to be explaining this in detail, this architecture. This blocks here are the so-called recurrent cells, and I'm going to be giving you examples of those, or one example of those. And so this, if you want, this parameter sharing is what makes this RNNs powerful and compact. And also enable you to have this variable length input. So that's how you say do this conceptual leap of going from this more traditional feed-forward neural network into the RNN with parameter sharing. So I'm gonna introduce recurrent neural networks as models for probability distributions. So this is not the only way you can use them. You can use them in many other ways, but this is, if you want, what I'm going to focus on. And so let's get started, like with the definitions and the math. So consider a probability distribution defined over a discrete sample space. So the sample space is sigma, where sigma are collection of variables sigma 1, 2, 3 to sigma n, and each of these sigma n can take d new values. So it can go from 0, 1, 2, 3 up to d new minus 1. So that's if you want a spin configuration, if sigma, like a spin 1/2 configuration, for instance, or spin easing variables, sigma, where like you have 0 or 1 or plus or minus 1, but you can also do like higher dimensional systems. So the probability of observing sigma, p sigma, is just this quantity here, p of sigma 1, sigma 2 through sigma n. And so one important thing that I'm going to be using is the so-called chain rule of probability, which allows you to write down p of sigma in terms of its conditional. So this is general, this is exact. So it's p of sigma 1 times p of sigma 2 condition on sigma 1, and so on, all the way up to p of sigma n condition on sigma 1, sigma 2, all the way through sigma n minus 1. So this is important and is the basis of how we build the RNN, okay? So I introduced this shorthand notation for the conditional sigma I condition on sigma 1 through sigma I minus 1 as sigma I condition on the sigma less than I, okay? This is a short for conditionals. So here, there's one important observation, which is if you wanted to specify every conditional in the chain rule, so this gives a full description of the of any possible distributions of this type, okay? However, this characterization is very expensive. In general, that representation, either directly writing all these probabilities or writing all the conditionals, is a representation that grows exponentially with the size of the system n, meaning that if you specify all the possible values for the conditional distribution, this is an exponential number of, it's a big table with an exponential number of entries. And so there's no hope we can use it for practical purposes, right? And the question is, can we alleviate this explosion? And the idea then is, yes, we will, and we'll exploit the structure of the problem to alleviate this complexity, which is something that we in physics we do pretty much all the time, right? Like for instance, in tensor networks, what you do is you have this exponentially complex, complicated wave functions, and then what you do is you write an approximation in terms of say matrix product states, which if you want alleviate that complexity. So what we do here is the same, right? Like, or is similar in that we're trying to alleviate this exponential complexity by exploiting some structure of the problem, right? And the idea is that nature is benevolent, and real world problems have enough structure that we can use it, like when we can use far fewer resources to solve these problems or to tackle these problems, right? And so RNNs, what they do is exactly that, which is they can parameterize this probability distributions p sigma entirely through the conditionals, right? Like, so basically what we do is we are parameterizing each of the conditionals in the chain rule here. Okay, so that's what the RNN does in this. RNNs do many things, but this is, if you want, the one way I'm going to be explaining them. So then the elementary building block of an RNN is so-called a recurrent cell, which is, if you want, helps us specify the conditional, okay? And the simplest recurrent neural network, people call it vanilla RNN because it's the simplest, it's just a nonlinear function that maps concatenation of a dh dimensional vector with an input vector sigma that represents the, if you want, the spin configuration or this variable up or down or 1 or 0. And then you map this concatenation through a nonlinearity, and then you end up with a new vector h n, which is this here. It's also dh dimensional. So that's all it is. It's a nonlinear function applied to a linear transformation or an affine transformation on this state vector or hidden vector concatenated with the input. Okay, and that's all that's all it is. And f is a nonlinear activation function, typically a sigmoid function. And then what are the parameters of the RNN? So it's a weight matrix, W with dimensions. They're usually real, but you can also use complex numbers. So it's DH times DH plus DV, which is, so DH is the dimension of this hidden vector, and the nu is the dimension of the input. Okay. And then the bias vector is it's in the RDH, so the dimension of the hidden state. So the state, so we're going to be using this expression as a recurrence. You go from a hidden vector hn-1 to hn. So this is a recurrent relation, and so we have to initialize h0 and sigma 0 to something to get the calculation going, and we initialize them to zeros, but any constant vectors work. And then something that I didn't specify is, like, I have this sigma in bold. I don't know if it was difficult to notice, but it's just a vector that represents each spin configuration. And what these are is they're so-called one-hot encodings of the input. For instance, so if you have some input that is either 1 or 0, then I'm going to replace that by like tiny vector with dimension 2, where 1, for instance, where 0 corresponds to 1, 0, and 1 corresponds to 0, 1. So that's, if you want, for convenience. So how do we proceed? So we proceed computing all these conditionals that I was mentioning in the chain rule through this expression. So each conditional sigma n, conditional sigma 1 through sigma n-1 is a dot product yn times sigma n, this one-hot encoding, where this dot is just the scalar product, and this yn is yet again an extra layer in the RNN. And I'm going to be explaining how this looks like graphically in a bit to make things a little bit more fun. So it's a softmax, so-called softmax layer, where you take this recurrent vector hn, you add this vector, and then you apply this nonlinearity called softmax. And so the softmax activation function is given by this exponential of the components of whatever you put there divided by the sum over the vectors, so that it is normalized.
Juan, there is a question related with the previous slide. I think we can stop and okay, we can go to the. Can you elaborate the condition on the dimension of the weight matrix? Why is that much specific?
Let me see. So on the condition, on the weight matrix. So
yeah.
So we have this weight matrix here, and so what it does is basically it contains the parameters of the model, and the dimensions of it is they're related to the power of the model, right? So it's here. So the power of the model, if you want the expressive power of the model, is encoded in this dimensional, like the dimensionality of the hidden vector h, which is this dh here, okay? And so this is tied to the size of the matrix, and so the dimensionality of this, if you want, this weight matrix is this one here, and it's tied to the expressive power of the model. I don't know if that answers the question. Maybe we can allow the Rajiv to be more specific.
Hello.
Hello.
Hi, you answered my question. Thanks a lot. Yes, I got my answer.
Okay, great. And then there's a question by Shayoni. So I was wondering where or how does the fact that the hidden layers are connected, the hidden layers enter the activation function. Let me see. So the hidden layers enter in the activation function through this expression in here. So so the hidden state of the model is age, right? And you apply this nonlinearity to the concatenation of age and that's how you process information in this architecture. And so yeah, so it goes through, yeah, indeed through the I mean, this is how the activation function is connected to the nonlinearity, is through this recurrent relation. Okay, hope that answers the question. Thank you all for the questions. So yeah, so I was here, I was at this extra layer of the recurrent neural network, which is the softmax, and the softmax ultimately provides the probability, the conditional, right? Like, because so this expression, as long as u and c are real, and as long as everything is real, then you have that this S, the softmax layer, gives you a conditional distribution or a probability distribution that we interpret as conditional. Okay, and that's how you get this conditional distribution. And then ultimately, you have done all this, like the computation of all this conditional sequentially. What you do is you can then compute the probability of the entire configuration sigma by multiplying. So the chain rule had all these multiplications, right? Like all these conditionals come multiplied. And so that corresponds to this multiplication here. So there's three important things that that I want to highlight that I think are very powerful about this model, which is, so one of them is the fact that P is normalized, okay? As opposed to, for instance, like energy-based models or probabilistic models based on an Ising Hamiltonian, where you need to compute the partition function if you want to get, say, P of sigma, which is very challenging for some of these models. So in this case, there's no issue. You can, I mean, the model is normalized, which is, I think, a very powerful thing to do. And then sampling the probability distribution is achieved in a sequential fashion. So you sample each conditional sequentially, and then at the end of that process, which you do, say, n times, then you are guaranteed you have an exact sample of the model, okay? So there's no need for, say, there's no need to perform more Markov chain Monte Carlo simulations to get samples from this model, which is, again, very powerful, I think. And so I wanted to highlight those two. So this is a graphic representation of the RNN. So here's the input. You send the input to the cell, which is this expression here that I was referring to. You compute this recurrence, and then you use this vector Hn to compute the conditional using the softmax. And at the end, you get this nice conditional, this parameterization of the conditional. This is, if you want a graphic representation of the fact that this cell is used on and on. So you take this Hn minus 1, you send it to the recurrent expression, and then you get Hn. So this is a graphical representation. This is the most compact. But there's also an unrolled version of this cartoon, which is you initialize at H0 and sigma 0. You do this little calculation in terms of this recurrence relation and softmax, which gives you the conditionals. You get P of sigma 1. You then use sigma 1 to compute P of sigma 1 condition and sigma P of sigma 2 condition of sigma 1, and so on. So this is kind of like an unrolled version of the recurrent neural network, where each box is either this expression with the corresponding hidden vectors Hn minus 1 and Hn and the parameters of the model. And this is how you, like, if you want, how you compute this distribution, right? Like P sigma, you just take, for instance, if you're computing the first term in this expression, what you do is you take this y1, the computation of the first step of the RNN, and you multiply it by sigma 1, and so on. You keep doing this on and on until you get all the distribute, like the value of the probability of some configuration. Maybe there's 3 questions. Maybe I can answer them right now. So I was wondering if the activation function relate to the partition function and what. So the question is, I was by Joseph. So I was wondering if the activation function relate to partition function and why. And I think so it does, right? It relates to the partition function because when you compute the partition function, it's a sum over all the possible values of sigma, and that gives you 1 that by construction. And so let me see. So, okay, the model is normalized by construction, so the partition function is not even there. But if there was a partition function, you could write it in terms of the activation function. That's what I think. But the partition function is, I mean, the model is normalized, so there's no partition function per se. And the second question is, do you apply any cutoff on the conditional probability? Okay, so this is a good question. So do you apply any cutoff on the conditional probability? Say P of sigma n is equal to P of sigma n condition only on, say, a few of the variables. And the answer is so in principle no, but because I mean, we never apply this so-called Markov condition, so we don't use it in the definition of the model. But in practice, as you process information, this vector h that is passed between the different steps in the unrolling of the RNN, I mean, this can only carry a certain amount of information. This is why this vector is called memory vector. And so in practice, what happens is that if you have a dimension dh of the hidden vector that is not too big, then practically the correlation between one variable sigma, say sigma 1, and the correlation between some sigma I, so 1 plus say 10 becomes weaker and weaker. Okay, it's actually, I think for most architecture, it decays exponentially. So it's similar in the sense, yeah, so it decays, right? Like it depends on how powerful the model is, but in practice, there's some cutoff, right? It's just that this cutoff is not imposed by hand by using some of these Markov conditions that Mahmoud is talking about. That's a good question. So maybe I can answer one more. So the statement that the samples are uncorrelated is really powerful. How does this relate to numerical precision when calculating an observable in comparison with Monte Carlo methods? So this is a good question. So the idea is that when you do Markov chain Monte Carlo, you have some autocorrelation time that you have to, if you want, use or to explore, such that when you compute expectation values using the samples out of a Markov chain Monte Carlo are correct, right? And the idea is that if you don't explore that and you use correlated samples, then you start introducing a bias in the expectation values of your quantity of interest. What I'm saying is in here, this autocorrelation is 0 basically, and so you know that given the architecture you have, given the model you have, this expectation values are unbiased, right? Whereas in Monte Carlo, in general, they are biased. If you because I mean, guaranteeing like that you're not using correlated samples is difficult. Though in practice, what we do is we do some sort of binning analysis so that we make sure that the samples are really uncorrelated. But what I'm saying is that you just don't have to worry about this type of analysis anymore because the samples are uncorrelated. So that's a good question. There's also one question: at what condition this becomes unstable as nonlinear signal is being considered? I'm not sure I understand the question. Can you speak, Sri Harsha?
Yes, here in this scenario, you are trying to use the sigmoid function, right? Which is a nonlinear signal.
Mm-hmm.
So at which condition this becomes unstable? So there are, if you are considering like dynamical systems or in this case, like there will be like some stability. At what point of time this system is stable, and what point of time this becomes unstable? What is the condition?
So I don't have a good answer to that question. So, but I understand. So this
Makes sense or not, I'm not sure, but I just wanted to give you a try, whether it is correct or not.
no, it is correct. And so I think so. I don't know of examples where this happens. So I understand where you're coming from. This can be understood as a dynamical system, but as far as I know, for this systems that I know, every time. So you can also think of this as a map, right? It is a map, right? Like and so what you like typically what happens is you flow toward some fixed points. That's what like what happens in my experience is you always flow to either A or B point or C, right? Like so I've never seen instabilities, right? Like what I see is some form of saturation in this models when understood as a dynamical system.
Okay, fine. So this area still needs to be explored, right? This point of concept has to be still explored.
I think there's some work on this along like the dynamical properties of RNN, but I'm not very familiar with it. But in practice, I've never seen because everything is properly normalized. There's no there's no explosion of anything in here.
Okay.
Okay,
This one will be in periodic sense, or this one will be non-periodic? Any condition?
I don't think it's not periodic, as far as I know.
Okay. Thank you. Thank you.
Yeah, no problem. So there's also a question. So can sigma be a matrix? I think so. It can be a matrix. You can indeed reshape. I mean, anything can be a matrix in some sense, but yeah, it can be a matrix. All right, let me go ahead. That I'm running out of time. So this is how we compute this. Then how you sample is a little bit similar, right? Like, so what you do is you initialize H0 sigma 0. You compute the first conditional P sigma 1. Then you sample this. You can use a random generator. And this is just a sampling either up or down. And you're given the probabilities. You sample, you get sigma 1, like the first sample, sigma 1. You bring it here, you input sigma 1 here, and you compute P sigma 2 condition on the sigma 1 that you observed here. You sample again, this is again two numbers, P of probability of up and down. If this is a two-dimensional system, you get sigma 2, you store it, you bring it here, sample P3 condition on sigma 2 and 1, you get sigma 3, you bring in here, you keep repeating this on, and this is how you get a sample. So it's very easy to, and it gives you exact samples, as I was saying. So that's it for probabilities. Let me quickly go through how can you send this to quantum many-body systems, okay? Which is the next part, which is RNN wave functions. So there's an important, so let me first tell you about an important class of so-called stochastic Hamiltonians or stochastic many-body Hamiltonians. They have ground states psi with strictly real and positive amplitudes in the standard computational basis sigma. So now I'm promoting sigma to quantum basis, if you want, or basis set. And so now there's this ket. And so you define the ground state of a stochastic Hamiltonian like in this form, and you can interpret that ground state as the square root of a probability distribution without but like when you restrict to ground states of Hamiltonians that are so-called stochastic Hamiltonians. And so it is natural then to use the recurrent neural network to represent these wave functions, right? So what you're doing is kind of like a coherent superposition of the RNN, and that's our RNN wave function, which we explored in this paper by my graduate student, Mohammed Hibat Allah. So However, wave functions are complex in general, and so we need a phase. And there's a simple way to introduce a phase. So let me tell you about how we did it. So what we did was, so this is the usual the RNN that I explained a little bit earlier, where we just make a coherent superposition of the probabilities, right, or the square root of the probability. So you can define a wave function or this wave function through the usual RNN. However, if you want to have a complex value wave function, what you can do is you can add an extra layer on top of the softmax. So here we have the softmax layer, which is what we had originally. Now we have a so-called soft phase or soft sign layer that computes a phase or a phase give for every conditional. Okay, and that's what we've done here. So it just adds a few more parameters to the RNN, and then you use those parameters to estimate some phase, phi1, phi2, phi3, all the way through phi n. And then let me give you the details. So the soft sign layer, we call it soft sign, is basically this expression here. You use you multiply by pi times this soft sign function, which is basically this expression here. It's x divided by 1 plus absolute value of x. So this is between -1 and 1. And so if you multiply it by pi, it looks like a phase. And then the overall phase of the wave function is just the sum of all the phases at each site or at each spin. Okay. So now let me, I think in the last few minutes I have, let me tell you, so that's all about the architectures and the basics of the RNN, but let me tell you how to train these models. And I'm gonna give you hopefully 2 or 3 examples of how you can train this. So in machine learning, which is that, if you want the traditional way people do it in machine learning, is you take a big bunch of data from a probability distribution you observed in nature, such as like images on the internet or a collection of words in a book, and then you can do the so-called or use the so-called maximum likelihood estimation or maximum likelihood principle. And so what you can do is to estimate the parameters of the RNN, we can use this principle. This principle is very simple. It's but also a very deep idea. So the parameters of the statistical model, which is our recurrent neural network, are selected by assigning high probability to the data you observe. So this makes sense because you imagine you're sampling some probability distribution, for instance, the probability distribution of natural images, so the images you take with a camera, and so what you get out of the camera, it's I mean, it has high probability of occurring because it happened, right, like in nature. So that's the idea, that when you sample experimentally from a probability distribution, the observations that you see have high probability, and so we should assign them, if you're feeding that data to a probabilistic model, we should give them high probability, right? That's the idea. That's the principle of the maximum likelihood estimation. And so you're given a data set, sigma hat, which is a collection of data points, sigma n. And then what you do is you compute the probability of that data under the model. And that's called the likelihood. Okay, so, and you assume that these samples you got in the data are uncorrelated. Okay, and so the probability of observing that data set is the product of the probabilities assigned by the model P theta. So P theta is going to be the RNN, and where the parameters of the RNN are encapsulated in this variable theta. Okay, so that's the idea. So you can maximize this quantity with respect to theta. However, it is so since probabilities are between 0 and 1, if you multiply too many of them, this likelihood function is going to be eventually very small. Okay, and so what you do is you say, okay, instead of using the likelihood function, I'm going to define, for numerical convenience, the negative logarithm of the likelihood. Okay, which is simply you take the minus the log, and then you end up with this expression here, okay, which is way better to handle numerically. And instead of maximizing the likelihood because you put a minus sign here, then you minimize this negative log likelihood, okay? And what you do is you use gradient descent techniques, which you saw, I think, last week. Okay, so what are the ingredients of this optimization or this minimization using gradients? So first you have to compute the gradient, the data of this negative log likelihood. And then you, to do that, you use some like algorithm called backpropagation through time, okay, which is basically using the chain rule on that function defined by the RNN, okay? So I have the slides at the end, but I won't have time. It's already clear to me that I won't have time. And so let's just leave it like that, but I encourage you to take a look at this link. It has a derivation of this backpropagation, so basically the derivation of the gradients of the RNN with respect to its parameters. And this is a course by a colleague of mine, Roger Gross, very, very clear. And then what you do is you do a parameter update following the direction of the steepest descent, which is basically you replace theta by theta minus some small parameter alpha times the gradient, and you iterate this until you get a convergence, okay? The hard part is using these derivatives in optimization because they can explode or vanish. And this is related to the question about the stability. So there's no problem in the calculation of the probabilities, but the gradients can become very high or very small. And this is, if you want, a consequence of like understanding this system as a dynamical one. And then for the point of view of the gradients, there's some issues. And so you need to optimize the architecture so that this is improved. And then finally, we're going to be using as a different method of training in physics, we're often given Hamiltonian, right? Like we're not given data, but we often have the so-called Hamiltonian, and so we can use variational Monte Carlo to optimize these answers with respect to some local Hamiltonian.
Juan, maybe before you continue, because there are questions related with all the learning stuff with maximum likelihood.
Oh yeah, yeah. Let's. So maybe before I go on with the questions. So how much time do I have? Do I have? It's already a break now, right? Or in a few minutes?
No, not necessarily. I mean,
okay.
I think you have till 3.
Okay, great. Okay, so then I'm gonna have enough time. Okay, awesome. So let me go ahead with the question. So as Lavi Kumar is asking, as you mentioned, RNN is concerned about sequential data. Can we determine the time dynamics of the system? For instance, wave functions sequenced in time. So I think I'm not sure exactly what the task is here, but yeah, so you can determine some time dynamics in some systems, and this has been explored. There's exploration along those lines of like using RNNs to explore real, like some time dynamics, right? So let me go ahead with a different question. So Sandeep is asking, during sampling, is it necessary to take account of fluctuations in sampling because sigma 1 is fed into next step sigma 2, and as you have said, there is random probability sampling. So yeah, so you so when you're doing sampling, yes, you account for the the probabilistic nature of what you're trying to do, which is sampling. So actually, so you output this, say for instance, P of sigma 1 in the first step, and then you do a sampling step. So you roll a coin or you roll a die, and then depending on the outcome, you can get either up or down, and then you take that and you bring it back to the RNN to compute the condition, the P of sigma 2 condition on that outcome. Okay, and so if you repeat this multiple times, you will see sometimes you see up, sometimes you see down, and so you would have accounted for this fluctuations that Sandeep is mentioning. Is there some stochasticity in gradient descent? So in principle, in gradient descent, depending on how you, on your cost function, on the training style, there's going to be a stochasticity. So if you have a data set that is too large, then like you would say, for instance, instead of taking the entire data set to compute this log likelihood, you would take only a fraction of it and use that to estimate the gradient. And so as you change the different like pieces of data, then there's going to be fluctuations due to the fact that you're not using the entire data set. But if you use the entire data, then there's no stochasticity in maximum likelihood estimation. But if you're doing variational Monte Carlo, then there's going to always be stochasticity because you cannot sum over the entire Hilbert space, and so you will have stochasticity in the gradient. So that's a good question. Thanks. Valentin, will it work for any kind of Hamiltonians or any or only local Hamiltonians? So yeah, so this is for variational Monte Carlo, this is meant only for local Hamiltonians. If you have a non-local Hamiltonian, then there's an intractability in a calculation of the gradients and on the calculation of the expectation value of the energy. So yes, so it's local. And then second question, how the dimension of H define physical reason. So the dimension of the RNN is so-called hyperparameter. It's a parameter that you fix by hand. And what people do in practice is the higher, the better, because it makes the model more and more powerful, okay? And the physical reasoning is because this H is the, if you want, is the mechanism through which you express correlations in a probability distribution or in a wave function. And so, if you have a physical system with strong correlations, then you want to make this dimension high. Whereas if you don't have any correlation, for instance, if you have a mean field theory, then this dimension can be zero, and this wave function becomes a mean field approximation. So this, if you want, that's kind of how I reason about it. Like if you make it zero, then this wave, this probability distribution is a product distribution, or in the wave function case, this is a mean field theory. And as you make this dimension higher and higher, then you account, you're capable of accounting for stronger and stronger correlations. Mahmoud, Mahmoud is asking, sorry, I did not understand what approximation makes RNN behave linearly with data size. I don't understand the question. I don't think I made the statement that they behave linearly with data size, but if you want to ask the question or clarify it, you're welcome to, Mahmoud.
Hi. In the previous lectures, reducing the size of Hilbert space by symmetric constraints or other locality constraints, we decrease the size of the data we need to run our calculations. I don't know what type of this approximation can be used here. My previous question in this post was the cutoff you apply on a conditional probability was in this respect. And I don't know, I don't understand the point here. Thank you.
Yeah, so we don't apply cutoffs, and the approximation that we make is that recurrent neural network representation cannot represent any conditional, unless you make this dimension of the hidden vector exponentially large, which we want to avoid. Okay, so if you made that dimension of the hidden vector very large, then you could represent, in principle, any probability distribution P sigma. Okay, so the approximation is that by restricting the amount of correlation or the size of the hidden state, you impose restrictions on the type of conditionals you can represent. So that's what makes the RNN cheap, but also less powerful than a generic approach where you do tables, for instance, which is exponentially big. There's a question by Tim. So for a sequence sigma 1 through sigma n, do we assume Markov property? I answered that question earlier, I think. So there's no Markov approximation. So there's an effective Markov approximation by cutting, like putting a fixed, a finite number in the dimension of the hidden state, which limits the type of, like the distance over which you have correlations. But in principle, you don't do any Markov approximation. I think this is a very important question, by the way. There's no Markov approximation. Effectively, something like that happens, but it happens naturally because you cannot account for very long distance correlations. There's a question by Lavi. So just to understand better, the RNN approach you showed here is for the sequential data of the system, for instance, calculate free energy as the temperature is decreasing. Then we determine the ground state, is it right? That means another way to determine the ground state. So it depends. So are you talking about the ground state of a classical Hamiltonian or the ground state of quantum Hamiltonian? And in both cases, you can do this, okay? You can do ground states with zero temperature of quantum many-body systems, but you can also use these approaches to compute the ground state of a classical Hamiltonian, which is an example that I have prepared for the next next session, like for the second part of the lecture. Okay. Okay, so I won't go through too many details of the RNNs with variational Monte Carlo. I'm gonna assume you have seen this, and I think you have last week. You can use variational Monte Carlo to estimate ground states of many-body Hamiltonians. And you do that by simply computing the energy and its gradients. Okay, the gradients are, they have this form. It's not too important. It's just we're going to be using the same technique, gradient descent, on the energy, expectation value of the energy of a Hamiltonian, a local Hamiltonian. And then we use the simplest parameter update. There are more complicated update rules like stochastic reconfiguration that I think Filippo Vicentini explained last week, and so on. But let me conclude with this, which is a beautiful example. It's related to a question I just got about whether you can get ground states of classical Hamiltonians, and can you use this to say, like for statistical mechanics problems. And so there's a way to do it, and it's described in this very beautiful paper by Wu, Wang, and Zhang in PRL last 2 years ago. So you can apply a variational approach to statistical mechanics. Okay, so what this is you have a model distribution P theta that approximates the Boltzmann distribution at a finite temperature T. Okay, so you may wonder why do you want to do this, but let me just bear with me. So what you do is basically you try to like have this probability distribution P match the Boltzmann distribution, and you can do this by optimizing the free energy of the probability distribution P theta, and you minimize it with respect to theta. Okay, so what is this free energy? Is expectation value of a classical Hamiltonian over this distribution P theta minus T times the entropy of the distribution, where H is the classical Hamiltonian, and the entropy, I'm afraid I didn't write the expression, is basically sum over the spin configuration sigma of P times log P. That's the entropy of the distribution. It turns out that if you use a recurrent neural network or any autoregressive model or any normalized model, such as the RNN, both the energy and the entropy are very easy to compute. Okay, so then you can use the same strategy to approximate statistical mechanics problems. Okay, so this is how you do it. So the free energy can be estimated from samples, and I explain how to obtain these samples from the RNN. And so basically you take NS samples, and then you compute this average over the so-called local free energy, okay, which is basically F log is equal to H. So here I have the word target because of something I'm going to talk about, but H, say classical, the energy, this energy of the classical configuration sigma, plus the log of the probability P of sigma. And as I said, I explained how to compute P, right? Like it's just this sequential process where you compute the probability of the RNN of configuration. So this is easy to compute actually. And then both the free energy, but also the gradients are easy to compute. Okay, it turns out that the gradients of the free energy you can compute using samples from the RNN. So you take NS samples and then you compute this one, the gradient with respect to theta of the log of P on the samples that you saw, times the local energy, this local free energy. And then what the thing that I haven't explained yet is how you get this gradients, which is again this backpropagation through time that I referred to the lecture notes of Roger Gross. In practice, we use automatic differentiation, which is a very powerful algorithm that allows you to compute the gradient of any differentiable program you write. So it is very easy to implement. It's almost you don't have to do anything. And then you use some simple parameter update. Theta equals theta minus a small constant, the gradient of the free energy. And you iterate this until convergence. And this is how you solve or you approximate solutions to statistical mechanics problems. I think that's it for now. And let's see if there are more questions. There are no more questions. And so I guess, I think, is it time for a break now, Alejandro? Alex?
Well, we can do a break now, I think. Some minutes as you need.
I can go on. It's up to you.
Well,
and if we
well,
want
I think if
break.
Yeah, let's do a small break, right, Tasia?
Yeah, I think we can make a break until, well, we have 50 minutes by the program, so
Yeah.
do that.
So we can have a coffee.
Yeah, I'm gonna have maybe a coffee. Or,
so see you again at 3:15, right?
Yeah. I'll leave everything open, I guess.
Okay, perfect.
And then if you have questions, you can type them in the Q&A, and I'll be back in 5 if there are any. Okay. Okay, thank you.
Perfect. Thank you.
You have another man. You have, I did. You have another man and you have another man. Oh, yeah.
Juan, you have a question in the Q&A.
Yeah, so it's just a very good question. So maybe I can have maybe I can answer it right now. Is that okay?
Yeah, why not? I think so. I mean, even we are.
Yeah, so this is great. So like, hi, I'm checking the GitHub source for the PRL 2019 you cited at the end for the easing model, and it says running this scripts may take thousands of GPU hours, produce hundreds of gigabytes of output data. So then why is it convenient to do it with respect to efficient Monte Carlo sampling techniques? Maybe only for example purposes. So that this is the key question. I really like this question. And so the idea is, key idea is in the question already. So with respect to efficient Monte Carlo sampling techniques, it turns out doing efficient Monte Carlo sampling techniques is not easy. And it's easy for the easing model, but if you say you want to tackle like a spin glass problem, then this efficiency just goes away because this Monte Carlo just gets stuck. And so the question is, if you do this variational technique and the optimization or the approximation to the free energy is good, or is actually, as they demonstrate in that paper, this is very accurate, then these autoregressive models can be sampled exactly with autocorrelation. Okay, so then at that point the question is, are you closer to the ground truth by doing approximate sampling with a very slow Markov chain, or with this free energy approximation, or this free energy bound, which is a model that you can sample exactly? Okay, and the answer is, for many of these problems, the approximation that you get out of the variational bound is better than the samples you get out of Monte Carlo. Okay, so I agree that maybe for the easing model, which we know very efficient algorithms, this is just an example, but for challenging for problems that are very difficult to sample, like spin glasses and other pathological models, this may be a tool that makes you, that allows you to make progress. Okay, I think that's my answer. I'm going to show you one example where, like, we're solving ground states of spin glass problems using this idea, and this works better than Monte Carlo. So stay tuned for my last slide.
So I think we can continue. It's already 3:15, so whenever you want.
Yeah, sure. Let's go ahead. Let me share my screen. Can you see my screen?
Yes.
Okay. So, okay, now, so I'm gonna go ahead and so it's recurrent neural networks for quantum many-body physics. And I'm gonna give you two examples of research that I've done using RNNs, one for quantum state reconstruction, and then one for variational annealing, which is that idea that I just explained roughly, or not roughly, but like closely related to the question I just answered, which is, so simulated annealing is a technique to solve combinatorial optimization. It turns out that what you do is simply use Markov chain Monte Carlo, or Monte Carlo on this problem Hamiltonians, and then what you do is you slowly decrease the temperature, and then you hope that at the end you find the ground state of the classical Hamiltonian, which is the solution to the problem. But for challenging problems, this dynamics of the Monte Carlo, the Markov chain, is very slow. So there's a chance that we can make progress with these models. And I'm going to give you an example of that. So let me start with the quantum state reconstruction, which is a little more involved. And before, so this slide is in the wrong place, but so I wanted to mention that last week we posted this paper, this neural networks in quantum many-body physics hands-on tutorial, okay? And so we described many of these techniques in that paper, even the recurrent neural network. But then the cool thing is we provided code that you can play with. It's very simple code, but it allows you to get started with all these ideas and so on. And so I encourage you to check this out. It has all sorts of examples: variational Monte Carlo, quantum state reconstruction, and so yeah. So if you're interested, if you want to learn how to code these things, then this is a good starting point, hopefully. So anyway, so let me go ahead with the quantum state reconstruction. So what is learning a quantum state, and what is quantum state tomography? It's the following. So quantum state tomography is the process of reconstructing the quantum state of a device by measurements. So you take a quantum system, you measure it many times, and then you try to infer what the quantum state is, okay? It is the gold standard for verification and benchmarking of quantum devices. And it is useful to characterize, for instance, optical signals. It's useful to diagnose and detect errors in quantum state preparation. For instance, states produced by a quantum computer. It can be used to detect entanglement and many more things. And the idea is that we need to go beyond standard quantum state tomography reconstructions, because there has been recent progress in controlling very large quantum devices, quantum systems. There's also availability of arbitrary measurements that are performed with relatively high accuracy. And so the bottleneck becomes progress in the estimation of these quantum states and the associated curves of dimensionality. So these quantum states, when we try to represent them in the classical computer, if you want, they entail using exponential resources in time and memory. Okay, so we need to go beyond standard quantum state tomography, which uses all exponential resources, and this is an important for the future of quantum simulations and the benchmarking of quantum computers and so on, and quantum simulators. So I have here trapped ions on top. Google processor, D-Wave is a quantum computer, it's a quantum annealer, and here I have cold atoms. So those are just examples of devices you may want to say characterize through quantum state tomography. So this is like the pace of growth. This is already a bit outdated, but this is 51 atoms quantum simulator, 53. This is 1,800. So this is, I'm very proud of this. I participated in this one, and quantum chemistry simulators and so on. There's lots of exciting and quantum simulations mostly that are becoming available and grow. And so can we find ways, or can we devise tools to benchmark this state preparations? So what are the ingredients? Quantum system that you can prepare repeatedly. So because, as you know, when you produce a quantum state, or as you may have heard of it, when you produce a quantum state, you measure, you destroy the quantum state. So you have to be able to repeat the same experiment many times. And then you need some availability of measurements that you can apply. So a set of measurements. And then you need a training procedure and a model. Okay, so a training procedure is you have a model for the quantum state, either a full representation of the density matrix, or a matrix product state, or a matrix product operator, or even a neural network. And then a training procedure that if you want, fits the measurements to this model, okay? And then at the end, you need a certification, kind of like putting a stamp on the model you train, which is, for instance, computation of the fidelity of the reconstruction with respect to an ideal state that you are trying to prepare in your quantum computer, and so on. So a typical tomography protocol prepares many copies of the state, and they're measured in multiple ways. Finally, the outcomes of those measurements are fit and produce an estimate of the quantum state raw star. Okay, that's the fitting part, and that's roughly how it goes. So here's one example of how you do this in practice. So this is called maximum likelihood estimation because it's the same spirit of what I was discussing. So it requires computing some probability, and you use this likelihood function that I discussed to fit a model. So what is this model? It's a physical density matrix in its most general form. So meaning that it scales like the representation scales exponentially with the size of the system. But then what you do is you assume that the measurements are independent, which they are, and then you compute the probability of observing these outcomes in the experiment, and you maximize this probability. This is the so-called maximum likelihood principle that we discussed. And then you fit the density matrix to the data, okay? It has some issue, which is exponential scaling in the parameterization and in the handling. So it's the time scaling of the processing of the algorithm is it's exponential, but this is the most reliable tool in the sense that it's the most general tool, but scales poorly. So you cannot apply it beyond a handful of qubits, say 10 or 12 qubits, I think at most, as far as I know. And so you cannot apply it for this large quantum simulators, okay? Then the question is how to make quantum state tomography efficient. And there are multiple ideas out there. So the most, one of the most interesting ones is introduce a parameterization of the quantum state with good scaling, but non-trivial structure. Like for instance, you can use a matrix product state of, or a matrix product operator, and then just do a reconstruction using this as your model for the quantum state. And this is, these two are like one of the most powerful techniques, is based on matrix product states and matrix product operators. However, there are other approaches that we came up with, which is introduce a parameterization of the quantum state with good scaling. So it follows that same trend, but use instead restricted Boltzmann machines or like neural networks in general, right? So this paper, which we co-authored a few years ago, we used a restricted Boltzmann machine and we performed quantum state tomography, okay? And this was extended later by Giacomo Torlai and Roger Melko, and they were able to introduce, if you want, a density operator that was written in terms of a neural network. So this is the reference 3 works for pure states with good structure, and it has good scaling in terms of the resources you need to use. And then this latent space purification approach handles mixed states, but has bad scaling, so it doesn't solve all the problems. So today I want to tell you about an approach where so instead of parameterizing the quantum state directly, we parameterize the measurement statistics of a measurement, which is given basically by Born buoy. And to parameterize that measurement statistics, so the probability distribution of the measurements, we use the RNN, okay, which is, I mean, the model that we discussed earlier today. And then we use this idea to learn synthetic states. So basically numerically generated experiments mimicking experimental data. So that's the idea with this whole approach. So let me tell you how to do this, but before that, let me tell you this. So it works for pure and mixed states with structure, meaning that it works for good. So it works well for quantum states that are well represented by a recurrent neural network, and it has good scaling in terms of the resources and so on, as long as this structure in the quantum state. Now, which states can we represent with an RNN? Still a little bit of a open question, but since RNNs are also universal function approximators, there's hope that as you make the RNN powerful or more and more powerful, that you're able to capture more and more quantum states that are interesting and so on. And the evidence that we have is that this RNN can represent a reasonable and non-trivial quantum state. So I'm going to show you examples of that. So let me remind you the setting. So it's so we have a large quantum device that we want to know if is working as intended. So we think this device can produce some non-trivial quantum states, and we want to certify that the system works in some simple cases, right? Like, so we have this device, we ask the device produce some quantum state, like, I don't know, like a matrix product state. And so we want to benchmark this preparation. This is useful in the near term, because as quantum computers become stronger and stronger, they're going to be producing quantum states that we cannot represent classically. That's the hope with quantum computing. So there's no hope that this is going to be working forever, but that we're going to be using it to benchmark near-term quantum computers or quantum devices. So let me discuss a little bit the theory behind what we're doing. So quantum states, measurements, and probability distributions. So a quantum state is traditionally described by a density matrix, which describes the statistical state of a quantum system in quantum mechanics. Everything we can possibly know about a quantum state is encoded in the density matrix. So what is this density matrix? It's a positive semi-definite Hermitian matrix of trace 1 acting on the Hilbert space. This family forms a convex set. Convex set meaning that all possible quantum states form a convex set, and for one qubit is the block sphere. So it's this sphere that we have here. In high dimensions, the shape of this convex set is not known, but it's known to be convex and basically be similar to a sphere, like a deformed sphere. So that's the traditional approach, but can we represent quantum states with just probability? That's what I want to do, and because I'm going to be using the RNN in its simplest form to represent it. So, and the idea is you can do this through measurements. That's why this is so natural for tomography, right? So, and measurements are described by positive by some operators M, right? We call them positive operator value measures, and they're, if you want, descriptions of what you do in an experiment when you go and measure the quantum state. Okay, so there this POVMs are just that represent mathematical representations of what you do when you measure a quantum device, right? There are collections of positive semi-definite matrices with a measurement outcome index A. Okay, for instance, A could be if I measure along like the spin along the Z direction, then you get either up or down. So this index A is that index, right? Like, is my measurement up or down if I measure, say, along the Z direction? And this operators sum up to the identity. Okay, so you go to the lab, you prepare the experiment so that you measure M, and your device gives you A, either up or down, for instance. So what is the relation between experiments and measurements? Is this expression here is called Born rule, because Born basically came up with it. Okay, so you have a quantum state you prepare in the lab row, you have a measurement apparatus that you use, you measure it, and then the probability that you observe A in the experiment is given by trace of rho times the measurement operator, the POVM element A, and that gives you this probability. Okay, that's the probability that you observe either up or down, for instance, in the lab. Okay, that's if you want a fundamental link between quantum theory, which is the description of the quantum state rho, and the description of the measurement, and what you see in the experiment, which is some probabilistic outcome of the measurement. Okay, so now I'm going to introduce the so-called informationally complete POVM, so informationally complete measurements. So, and what are these informationally complete measurements? It's basically a measurement or a set of measurements such that if you measure the quantum state with that apparatus, then you get all the information about the quantum state. And you can think of this as the following. Suppose you have, like, your quantum state is I don't know, a three-dimensional object, and then you want to understand that object, right? Like, so for you to do that, you have to take this three-dimensional shape and you have to see it from different directions for you to be able to see it entirely, right? Like, to characterize its shape. Okay, so informationally complete measurements are that thing, right? Are like, it's observing the quantum state from all possible directions such that you can determine what it is, right? Determine the quantum state. So this I like this analogy, right? Like, it's like observing an object from multiple directions. For instance, measurement that is not informationally complete for a 3D object is, I don't know, observing only along the X direction. That doesn't tell you what happens behind or above, and so on, right? That's the idea. So informationally complete measurements are a set of measurements that allow you to see the quantum state in all possible directions, such that you can draw a cartoon of this quantum state. That's how I think about this, or the simplest way, but or a simple way to think about it. So informational completeness means that the measurement statistics PA, which is, if you want, the observations, contains all the information about the quantum state. It also means the following. If you have a Hilbert space, then you can span it with this set of operators, right? Meaning that you can write any operator O as a linear combination of these operators MA. The final meaning that I want to highlight is that the relation between rho and the probability distribution P can be inverted. So here we go from rho to P. If you have informationally complete measurements, typically you can invert you. So you can write rho in terms of P, the probability distribution, so that P becomes the quantum state, if you want, okay? And that's what we exploit here. We exploit informationally complete measurements, and we represent the quantum state in terms of this probability distribution PA. So this is the inversion part. I don't want to go through the math, but the message is the following. Born rule tells us that you can go from the quantum state and the measurement to the probability distribution. If you have an informationally complete set of measurements, you can go the other way around, which is you can write rho in terms of the probability distribution P. Okay, that's the key element. And then the expression is this here. And what I have here in this representation is a tensor network representation of this expression, which is telling me that what we're doing here is factorizing rho in terms of probability distribution that is complicated, and a set of simple product of tensors that are very simple. They're factorized, right? So all the complexity and potential intractability of the quantum state gets pushed into the probability distribution, because that's what makes this distribution not be, say, for instance, a mean field, for instance. So all the interactions and all the entanglement gets pushed into the probability distribution, and that's what we exploit. So what we do, or the insight we had, was we can create a representation of the quantum state in terms of a probability distribution over an informationally complete set of measurements M, okay? And what we do is we use recurrent neural networks to represent this distribution P. And we know recurrent neural networks are very powerful, so that's what we use, right? So because first they allow for exact sampling, they have a tractable density, we can compute the probability of configuration A, and we can use maximum likelihood estimation, for instance, to learn the RNN if we have a data set of experimental outcomes. That's the idea. And so what we do, or what we have here, is a model for the density matrix, raw model, that is an RNN model here, which I call language model, because they're typically used in language processing. And then you attach a set of simple tensors. They're tiny, okay? And that's our model for the density matrix for the quantum state. So let me recap what we do, or what we would do in the lab. And we have done it actually in a recent paper. But so what we do is this: we prepare a quantum state repeatedly on a quantum device. Here's Google's processor, or IBM's quantum computer. We perform this measurement, this informationally complete measurement. This gives us a large collection of measurement outcomes. So it's a big data set. Then we fit the recurrent neural network using maximum likelihood estimation, exactly what I explained in the first part of today's discussion in the morning, or in my morning. Then we invert this density matrix. And I said, I use quote unquote, this is only a formal thing. Inverting this exactly is exponentially difficult. So we don't do it, but we can do it in practice if we want, for instance, to compute, say, correlation functions over the quantum state and so on. Or if we want to compute, say, fidelities, classical fidelity, and so on. And then we perform some sort of certification, either through fidelity, classical fidelity, or measuring correlation functions that are relevant for the system you're interested in. Okay, so that's what we did. So let me give you one example of reconstructing some numerically generated quantum states. So here is so-called pure G8Z state. So it's the so-called CAT state too. It's a superposition of all spins are 0, 0, 0, 0 plus all spins are 1, 1, 1, 1, 1. Okay, so that's this CAT state. The density matrix is this one here. And then we also introduce a model of noise, because so this is a pure state, but we also want to explore whether we can represent mixed states, right? And so we use a model, a noise model. And this noise model is the following. So with probability P, we apply an error on the quantum state, where we, with probability 1/3, we apply either sigma x, sigma y, or sigma z on the state. And with probability 1 minus P, we do nothing. Okay, so that if probability P of introducing an error is 0, then we are back to the pure state. But if we make P large, then we have a completely mixed state. Okay, that's the idea. So can we reconstruct these quantum states using a recurrent neural network? That's the question. And here's like learning only. So this is 2 qubits. And we apply measurements for different values of noise. And then we train these models, right? Like, so in here, I'm using a restricted Boltzmann machine first as a first example. And this is the KL divergence, which is basically the difference or the distance, if you want. It's not exactly a distance, but a divergence between the model distribution and the exact probability distribution of the measurement outcome. And this is as a function of training, as we train these models with using maximum likelihood principle for maximum likelihood estimation. And what we see is that as we train the model, this distance or this divergence goes to 0 for the different values of noise, P0 all the way through P is 1, okay? And so we successfully train this model. What we see is that training the distribution is harder for low values of noise, but easy for large values of noise, which makes sense because when you have high values of noise, this is basically a constant distribution. It's a completely random, completely flat distribution. So it's very easy to learn. There's nothing to learn. It's just one parameter. So this is the easiest to learn. So it goes to 0 faster. Whereas for low values of noise, it takes some effort, right? Like, so this is the KL. This is for the fidelity, which is basically the overlap between these two distributions, which goes to 1 as you train. And then finally, we have the quantum fidelity, which is the distance between the quantum states itself. And it follows the same trend, right? Like it goes to 1 as you train the models, meaning that everything is working. However, this was only for 2 qubits, and it was difficult to scale it to more than 3 or 4 qubits. So we said, how about we try something else? And we tried the RNN. And for the RNN, we were able to go up to 80 or 90, I think 100 qubits, which was pretty surprising. So we were very happy. And we thought this was very strong result. So that the RNN is capable of representing these quantum states in this form, like using probability. And what we have here is a function, like a classical fidelity as a function of the number of experimental outcomes that we use in the reconstruction. And what we see is that for small values of noise, then you see that as you add more and more data, you get a better and better reconstruction, right? You get higher and higher fidelity. And what we also see is that for high values of noise, you need less and less data for the same reason that learning a flat distribution is cheap, it's easy, right? You need fewer data points. The interesting thing is that for you to get a high classical fidelity, say for a value of 0.95, you only need a number of samples n star that scales roughly linearly with the size of the system n. So this is the number of qubits. So in that sense, this approach is, I mean, it has some scalability properties that are mild, right? In the sense that if you're trying to use this so-called classical fidelity, you can achieve high reconstruction accuracy with moderate resources, okay? And this is in part due to the fact that we're using this RNN, which is very powerful, and that we can represent many important distributions with it. Now we moved on to ground states of local Hamiltonian. So this was all for the GH set, but then we wanted to explore if we could reproduce ground states of many body Hamiltonians. And so this is for 50 spins, we use DMRG, the matrix product state, and we find that that we can also reconstruct these ground states pretty accurately. So this is the orange curve is synthetic data, so coming from density matrix renormalization group, expectation value of sigma z, sigma x as a function of the site. And what we see is that our reconstruction matches, like the correlation functions of the reconstruction match pretty well the synthetic data. Okay, and this is for two-body correlation functions, sigma 1, sigma I along the z direction. And again, we see a good agreement. Then we have a little bit more complicated model, which is the Heisenberg model on the triangular lattice, which, I mean, it's an interesting model in that it has a complicated sign structure, right? Like this is a model whose wave function is not known, and we know it has a complicated sign structure. And we wanted to see if we could represent that ground state with only probability, which is what we're doing. And so that's why we picked this example. So this is on a 8x8 lattice, and these are correlation functions of the synthetic state, namely the ground state of the Heisenberg model on the triangular lattice. And these are the reconstructions. So, and it seems to be working really, really well. So yeah, so that's it. So using the RNN, so kind of to conclude, so using the RNN was important for the success of the method because of its tractable likelihood and the fact that we can exactly sample them. Okay, as I highlighted. If there are any questions, now it's a good time to discuss. There's no questions, so maybe I can go ahead.
Yes.
Okay. So that was it for reconstructing quantum states. Now let me tell you about something newer. So this, there was a question. So can you explain why we can get exact sampling? Oh yeah, so this is from Kazuki. So how can we get exact sampling? Is because this RNN is constructed by parameterizing all the conditionals in a probability distribution P sigma 1, 2, 3 to n. So what we do is the model parameterizes each of the conditionals, meaning that we parameterize P of sigma 1, and then P of sigma 2 condition on sigma 1, sigma 3 condition on sigma 1 and sigma 2, and so on. So if we have all a specification of all those conditionals, then you can use the conditional at 1 to get a sample of P sigma of sigma 1. Then you can feed that into the conditional for sigma 2, and you can sample that conditional. And then you take sigma 1 and sigma 2, and then you compute the conditional on sigma 3, and so on until you exhaust all n spins. And so since you have access to all those conditionals, which is true by construction, then this is an exact sample of the model, and then that's why you can, just because of the construction of the model, okay? Which I think, yeah, it's very important. Okay, so if there are no other questions, oh, there's one more. So this is from Robertson. How does the measurement MA comes in the example of calculating ground states of Hamiltonians? Yeah, so that's a good question. So it comes in the following form. So what we do is we prepare, so we imagine we're preparing this quantum state, right, in a device. And then we measure this device or this quantum state, that is the ground state of the Hamiltonian, and then we collect the statistics, and then we reconstruct the quantum state. So we use basically the measurement outcomes of those measurement operators M to train, okay, the RNN model in these examples too. I hope that answers the question. Then let me go ahead with one more, Apolinario. So can Fisher information be used as an alternative measure for POVM? That I don't know. I'll have to think about it. It could be, but I'll have to think about it. All right, let me go ahead. Okay, so let me go ahead with the next. So this is new from a couple of weeks ago. So it's variational neural annealing. So let me introduce this idea of combinatorial optimization. So many important challenges in science and technology can be cast as optimization problems, right? So there are famous optimization problems that we use to motivate this, but say traveling salesman problem, nurse scheduling problem, vehicle routing problems, spacecraft scheduling, circuit design, discovery of the Higgs boson, all those can be recast, or the data analysis of this experiments or these problems can be recast as an optimization, okay? And these are computationally very difficult problems. It turns out that many of these problems can be formulated as finding the ground state of a classical Ising Hamiltonian that I call H target, okay? So this is the expression. So this sigma I, sigma j variables are just basically plus or minus 1. And this is extremely general. Like many problems can be cast as finding the ground state of this. And what is the ground state of this Hamiltonian is finding the spin configuration sigma I that minimizes the energy, or this ground state, this energy, or this Hamiltonian, okay? But finding these solutions is extremely hard for some problems, right? So there are heuristic methods to do it. And one of them that I really like is called simulated annealing. So what is simulated annealing? So it kind of like inspired by old technique. So it mirrors the analogous annealing process in material science and metallurgy, where a crystalline solid is heated. So you warm up a piece of metal, like a sword, and then you slowly cool it down. And as you cool it down, this piece of metal finds its lowest energy and most structurally stable crystal arrangement, which makes the material really durable and hard. And this is actually used in when people build weapons and swords, okay? So, and so people took, in the 80s, they took inspiration from this metallurgic technique to devise an approach to solve combinatorial problems of this form, basically finding the ground state of an Ising Hamiltonian. And so what they did was they defined this simulated annealing, because it's not real annealing. You don't heat up your computer or anything. You basically simulate annealing and explore this optimization problem's energy landscape by a gradual decrease in thermal fluctuations. But these thermal fluctuations are generated by Monte Carlo, by the Metropolis Hastings algorithm. So basically what you do is you take this Hamiltonian and you simulate it using Monte Carlo, okay? And then what you do is you slowly cool down the temperature of the simulation, okay? So you decrease the temperature little by little until you reach the temperature to 0, and then at 0 temperature, you should be seeing only configurations that are consistent with the ground state of the target Hamiltonian, okay? That's the idea with simulated annealing. It provides a fundamental connection between thermodynamics and the behavior of physical systems, but with complex optimization problems. So I think this is very appealing and a very beautiful algorithm. The problem with simulated annealing is sampling the Boltzmann distribution using Markov chain Monte Carlo or Metropolis Hastings algorithm becomes very slow for hard optimization problems as you cool down, as you make this temperature too low. And this is because the autocorrelation of the Markov chain becomes very large. Okay, so finding solutions to these problems becomes very expensive because you have to wait for a very, very long time. Okay, and this is a schematic cartoon of what happens, right? Like, so what you do is, so this is a simplex, so the space of probability distributions. And so what you do is you start at very high temperature somewhere here, and if you did annealing at a very, very slow speed, you would follow a path that connects infinite temperature with 0 temperature. So this, if you want, is the exact Boltzmann distribution at all those steps, and then you solve the problem exactly, which, like, the solution is either, like, for instance, for a degenerate problem, you find this configuration or this configuration. So that's if you do it very slowly. However, if you do simulated annealing, which is you do a Markov chain Monte Carlo, this Markov chain would go out of equilibrium, okay? So that I represent here, and then you get stuck somewhere here, and you end up with some approximate solutions, maybe good, maybe bad, okay? Now, that's what happens with simulated annealing. Now, what we're proposing is, here's one idea. So replace annealing and approximately sampling the exact Boltzmann distribution by annealing an approximate distribution that is close to the Boltzmann distribution, like an RNN, that can be sample efficient. So there's no autocorrelation. Okay, that's the idea. And then this may or may not lead to better solutions. So that's why this method is heuristic. But what we find is that this approximation to the Boltzmann distribution that we compute with the RNN is a better approximation to the exact Boltzmann distribution. And so it means that you can get better solutions than simulated annealing by using the RNN because of the fact that you can get exact samples without autocorrelation. Okay, so that's the idea, and this was posted on the archive a few weeks ago. And so let me show you one example of solving optimization problems with this technique. But before doing that, let me tell you how we train these RNNs, or how we optimize them. So how to train this RNN so that it mimics the Boltzmann distribution. That's what we want to do, and then anneal in temperature. So we use a time-dependent free energy. And then the nice thing is we'll have an energy part. This is the target Hamiltonian. We have a time-dependent temperature, which is kind of like this temperature that allows us to go from high temperature to low temperature, and then the entropy. That's going to be our cost function, the thing that we optimize. And then we start at high temperature T0 and use a linear schedule function T, such that as we make T, small t, larger and larger, all the way from 0 to 1, we end up at the ground state of the problem. And then what we do is we optimize this free energy. Okay, so what is the algorithm? We perform a warm up at high temperature, where we make the RNN match the high temperature distribution. Then we do small time steps, and we retrain the model at each temperature. Okay, and we use the variational parameters from the previous step on the model at the next time step, t plus delta t. Okay, and then at the end of the annealing process, this distribution given by the RNN is expected to assign high probability to the configurations that solve the optimization problem. So that's the strategy. So these are the results. So let me highlight, for instance, figure A. So this is for a spin glass problem with, I think, with 100 spin. It's called the Sherrington-Kirkpatrick model. And it's a fully connected spin glass problem, so it's deemed to be challenging. And what we find is that as we make the number of annealing steps, meaning the time we take from high temperature to low temperature, what we see is that the residual energy, right? Like, so meaning the energy, the excess energy with respect to the exact solution to the problem goes to very small numbers, basically around 10 to the minus 6 for variational simulated annealing. So basically for our technique, which is this thing in blue. Okay, and it does so at a faster rate than traditional simulated annealing, which is this red curve here, and even simulated quantum annealing, which is also a powerful method inspired by quantum annealing, actually. And we find that this technique is, like our technique, is significantly better if you put a lot of annealing steps. So this is for the Sherrington-Kirkpatrick model, and this is for a so-called Wisher-planted ensemble. It's also a fully connected spin glass. This one is very interesting. It's very difficult to solve, but we also find that our method, if we allow enough annealing steps, we find solutions that are orders of magnitude more accurate than simulated annealing, as well as simulated quantum annealing. And this is, again, one more example of the Wisher-planted ensemble, where we also find, I mean, we find better solutions, but not as accurate as in these two other examples. And with that, let me conclude and take a few questions. So we introduced a formulation of the quantum state that is closer to statistical theory, because we represented the quantum state in terms of probability. We use that representation to reconstruct quantum states of increasingly large sizes. And so it provides a way to approximately reconstruct these quantum states. And then for the final part, we introduce a variational formulation of simulated annealing that produces very accurate solutions to spin glass problems and may have applications in all these areas. And just to conclude, I have this personal belief that there are a lot of opportunities at the intersection between physics, condensed matter physics, and machine learning. And with that, let me take questions.
Thank you, Juan. So yes, you have 2 questions already. Okay.
Hi, dear. Is it possible to get the slides of these courses? Yeah, I can send my slides to the organizers, and then
we will post it in the webpage of the event.
Okay. And then there's a question by Yusuf. Could we use variational annealing to construct states ensembles in case of quantum steering? So I'm not familiar with quantum steering. So can you explain it to me? Maybe we can allow Yusuf to speak.
Yusuf, do you want to talk?
Good evening.
Hello.
Thank you, Juan, for the presentation. The quantum steering is a correlation between the null locality and the entanglement, and it's used to secure the communication, the quantum communication. If I am could you understand me, or I need to clarify?
I think I want to understand what is it that you want to do? I'm not sure I understand. Yeah.
So what the case when we have the case of entanglement, we have 2 trustable parties. If we, for example, Bob and Alice, but in the case of steering, we don't trust one of them. So Bob send their states, and or Alice send their states, and Bob need to check them and need to construct the state. And maybe we use in the normal case we use the semi-defined programmation to optimize the state that Alice is sent to Bob.
Mm-hmm.
So
yeah.
could we replace the state the semi-defined programming by the variational method?
Yeah, so I think I now understand. So I think that as long as you can formulate this problem as a combinatorial optimization, or as a finding the solution as finding the ground state of a classical Hamiltonian, then you can use it.
Thank you very much, Juan.
Yeah,
yes.
The question is, can you reformulate it that way? And if yes, then you can.
Thank you.
Okay. There's a question from Giancarlo. So can you study metastable states, local minima and free energy barriers, and characterize the free energy landscape with this variation? So I think that's a good question. I think yes, right? Like you can try to do that. The problem is, or the problem that I see is so the training, so the optimization of the free energy may fail. Okay, and there's no easy way to check for that. But we with my student, we think there's a way to solve this issue of like mode dropping, which is basically missing some of the local minimum. But I think the method itself doesn't guarantee that you would find all the modes of the distribution, or that it's going to explore all the like the entire landscape. But I know people have tried this for like this, perhaps this style of approaching these problems using machine learning. So I think there is hope, and there's potential to approach this type of problems with these techniques with annealing. Thanks.
Okay, there is a question also in the chat. Could you share references for and source for spin glass solution with variational SA?
Let me.
In the chat.
I didn't hear very well, but let me.
Okay.
Let me read it again. Could you share reference and source? So the reference is. Let me share again. So the reference we have is this. So archive 2101 10154. And the source, we have not released it yet, but we will do it. Okay. However, this is very easy to code. So if you go to the hands-on tutorial, there's an RNN already there, and you can change. So this is basically a loop over, like the simulated variational simulated annealing is just a loop over different temperatures when you try to optimize the free energy, which is easy to compute. And so there's plenty of code that is available to do this. And even in this hands-on tutorial, there's already code to do it. But we'll eventually release our code in here for spin glasses. Any more questions?
Yes. There is another question in the Q&A.
Yeah, so Robertson asked, I'm not sure if I missed it, but how do you verify results thrown out by the algorithm, for instance, in the spin glass problem? So, and this is a good question. So for the spin glass problem, so for the Sherrington-Kirkpatrick, we use the so-called spin glass server. So there's a server, I think this is in Germany, Jülich, where you just give them the problem Hamiltonian and they give you the answer. They use some heuristics and they tell you, yes, this is the answer, or like they tell you we cannot solve it, either because it's too big or there's no heuristic to do it. And so for the Sherrington-Kirkpatrick model, we use the spin glass server, and for the Wishart ensemble, so the Wishart ensemble is very interesting. It's a fully connected spin glass problem with so-called planted solutions. And planted solutions, what that means is that the solution is known to you by construction. So it's kind of like finding a needle in the haystack where you know what the needle looks like. It's just that the needle is surrounded by straws, by a big bunch of like haystack. And so the energy of the straw or the haystack, they're very, very similar, really close in energy to the energy of the needle. Okay, but you know what the needle is, so you know the solution. So you don't. So the way you verify the solution given by the VCA, but the variational simulated annealing, is because you know the exact solution. You're just trying to find it in a, say, rough landscape of similar states surrounding it.
I see. Thank you. But what if we don't have that known solutions?
Then you just hope for the best. Yeah. Many of these problems have no known solution. I mean, if we did, then there wouldn't be problems, right? Like they won't be optimization problems. You just knew the solution then. But for many of these problems, what you do is you try and you find the best energy you can, and then you take it. And then, yeah, that's how it works for some of these problems. There are bounds for some algorithms. So some algorithms can tell you you're this far from the real ground state, but not all of them. So in our case, this doesn't tell you it doesn't give you any guarantee. It's a heuristic.
Okay, if there are no more questions, I think we can finish here. We have plenty of time, so if people want to ask you yet, but if not, thank you again, Juan.
Yeah, thank you very much. It was a pleasure.
Next time you came here,
I hope
we meet you
so,
in Trieste. And that's all. Well, I don't know, Asia, do you want to say something for concluding this series of machine learning?
Yeah, I hope it was very useful for all the participants. It was definitely useful for me because I'm also working so much on this subject. And so, yeah, thanks to Juan and to all the previous speakers and tutors also.
Yeah, thanks for having me. And yeah, it was fun. And yeah, hopefully we'll see each other in the future somehow.
I learned a lot, so thank you very much.
Thank you.
Thanks to everyone. So yeah,
thanks.
We conclude.
Let's stop here. Yeah. Bye.
Bye, everyone.
Bye.